Okay, in this next set of notes, we get some really amazing results that really reveal how thermodynamics connects very different types of quantities that we might not think are related. For example, one thing we'll be able to do that we haven't done before is figure out how entropy varies with pressure for a solid or a liquid. We haven't done that calculation yet. We've assumed it's basically independent of pressure, but we'll be able to check that assumption. This will also help us analyze phase diagrams, sort of completely understanding all the different equilibria that you've seen on phase diagrams in general chemistry or general physics, maybe. So we'll derive these four fundamental equations for our sort of four key thermodynamic variables: energy U, enthalpy H, Helmholtz free energy F, and Gibbs free energy G. This gives us those really nice results. So let's get started. This first one here, I sort of have shown the derivations. We'll just talk through it very briefly. So again, this will help us calculate our thermodynamic variables under any conditions. The trick here is that let's consider a reversible process and do no non-mechanical work. If we apply the first law to that situation, we have du is d bar q reversible plus d bar work mechanical reversible. And the really fundamental insight here is that if it's a reversible process, we have nice equations for each of these. d bar q rev is ds is equal to d bar q rev over t, so d bar q rev is t times ds, which we can substitute in there. And mechanical work is normally negative p external dv, but again, remember, since we're at, right, that's true, but if it's reversible, we have p external is equal to p, so if we have d bar work mechanical reversible, that's going to be equal to negative p dv. If it weren't reversible, p external wouldn't be equal to p. So as a result, again, I'll put that in, highlight that here. That's that second term. We get this really powerful result that the change in internal energy U is equal to TdS minus PdV. And this applies, again, no matter how I'm going to change the internal energy, I can always write it in this way by considering this reversible process. There's now nothing depending on the path in there at all. Now, using calculus, what this means is that U, if I consider it a function of entropy, volume, and moles, then we have the du over ds, if I hold volume and moles constant, is going to be equal to T. Again, the idea here is that, again, if volume is constant, dV would be equal to 0, and so du over ds is just equal to T. What this actually gives us right off the bat is a real thermodynamic definition of temperature. We actually haven't defined that thermodynamically so far. That was the one thing we had sort of not precisely defined macroscopically, but now we have that definition. It's seems maybe a bit unusual. It's how temperature is du over ds at constant volume. And similarly, we have a macroscopic definition of pressure. du over dv at constant s is equal to negative p. So again, this definition of temperature is something we're going to come back to. It's a really powerful idea that temperature is basically a measure of how we can view it this way, or if we flip this, we'll see that we can view it as a measure of basically how much extra entropy do I get for every unit of energy I add. That's really what temperature means. Okay, moving on to our next derivation. For the Helmholtz free energy, F is U minus Ts. So dF is equal to du minus Tds minus SdT again, where Ts, if I take sort of the total differential of that, I use my product rule to get SdT plus Tds. That's sort of the idea here. since du has this nice form here, the fundamental equation for internal energy is TdS minus PdV. I plug that in for du, and I get some nice cancellations here. TdS cancels, and I get dF is equal to minus PdV minus SdT. So again, this now lets us figure out changes in free energy with no reference to the path. We just have these nice results here that just involve changes in our thermodynamic variables. Okay, the next one here, we'll get the corresponding equations for H and for G. Yeah, you can definitely take a minute to try to do these. They're not, they're very similar to what we've done before, and then I'll show the solutions in a minute here. Okay, so first for H, I have dH is equal to du plus P dV plus V dP. dH is equal to, again, my fundamental equation for internal energy was T ds minus PdV. So again, that's substituting in from above, plus PdV plus VdP, and we'll see that we get a nice cancellation here. So these two terms cancel, and we get a final result. dH is equal to TdS plus VdP. And this is our fundamental equation for enthalpy. Now, similarly, since the Gibbs energy, G is equal to H minus Ts, if we sort of apply a D to everything there, dG is equal to dH minus TdS minus SdT. Again, same approach we took before. dH is equal to that, so we'll plug it in. dG is equal to TdS plus VdP minus TdS minus SdT. And again, if I go through and see what cancels here, my TdS cancels, and I get, again, another very simple, straightforward equation for how Gibbs free energy changes. Just in terms of thermodynamic variables, I get VdP. I'm going to write it in the other order because generally we write the entropy terms first. So this is negative SdT plus VdP. We can see that all of these four equations involve S, T, V, and P in some combination. There's different ways you can, get these. These are just going to be on our equation sheet because they are so powerful and help us solve so many problems in thermodynamics. So those are our four fundamental equations. Now let's see what we can do with them. Okay, so if we're going to apply this, previously we assumed that G bar was independent of pressure for solids and liquids. Now we'll be able to see if that is actually true. So how does the free energy of an incompressible solid or liquid vary with pressure? We'll use that to figure out what is G bar, delta G bar for water at 4 Celsius, going from 1 bar to 100 bar. How big of a difference actually is there in free energy? Okay, so the first thing we're going to do is we apply our fundamental equation. This is going to help us determine how G varies with pressure at constant temperature. We can see that's right there in the variables there, so this is very convenient. First, we'll convert to molar quantities, so extrinsic X goes to an intrinsic X bar. So dG bar, the change in molar energy, is V bar dP minus S bar dt. Since we're at constant temperature in this process, we can cut that term and take it out, and we get a very simple equation. dG bar is equal to V bar dP. And now we can actually do this calculation. The assumption here is that Water at 4 Celsius, okay, what do we need to know? We need to know the molar volume. Water at 4 Celsius has a density of 1. And again, I'm going to assume it's incompressible, so that's going to mean the volume here stays constant as I increase the pressure. Not exactly true, but a pretty good approximation. And again, water's molar mass is 18.02 grams per mole. So if I plug that in, I'm going to get 18.02 milliliters is equal to V bar for H2O under these conditions, which again, now I do need to sort of be careful about my units. I'm going to do that in liters, 0.01802 liters. So now if I want to know delta G, again, I can just integrate this. Integral of dG bar is equal to V bar dP, integral from Pi to Pf. On the left-hand side, that's my delta G bar. On the right-hand side, since I'm assuming V bar is constant, that can come out of the integral. So this is just going to be V bar, and then what's left in the integral here is just dP, one of our favorite integrals. So V bar delta P is what we had here. And then I can plug that in. So this is going to be equal to 0.01802 liters times my pressure change. Went from 1 to 100 bar, so that's 99 bar. And again, I want to get out of liter bar and go back to, say, joules, a better energy unit. So times 100 joules per liter bar. And I get delta G bar is equal to 178, what do I have, 3, 4 sig figs, 178.4 joules, I guess per mole here, because we still have a per mole hanging around from V bar as liters per mole. And again, is this a big change? Again, not much. I mean, 100 bars is a pretty big pressure. This is only 0.2 kilojoules per mole that it changed its molar free energy by. So again, not nothing. We went up to a pretty big pressure. We can see that delta G bar is equal to, if we keep pressure constant and change the temperature, this is going to be negative S bar delta T, again assuming that S bar is constant with temperature, which isn't true, but is at least approximately true. So if we do the math on this, this is sort of similar to about a 2.5 Kelvin change in temperature. And again, 100 bars is quite a high pressure. That's, a lot more than the normal pressures we're working with every day in the lab. So yeah, generally a pretty small difference here as we're creating a little bit of gas going from, 1 bar of pressure to 2 bars of pressure, or from 1 bars of pressure to 0 bars of pressure in the lab. Not normally much difference for solids or liquids. Okay, the next one here, and this was right? This was an example of one of these hidden relationships. It turns out that free energy, which seems like, doesn't seem like it should necessarily be delta G should be equal to V bar times delta T, but in this case it is. And again, V bar and delta P are just sort of pure mechanical measurements, measuring the volume of a substance and measuring the pressure. No calorimetry needed, again, just pure mechanical measurements on its pressure and volume. So this turns out to be one of the key advantages of these fundamental equations. They reveal these hidden relationships between variables, connecting things that are easy and hard to measure. So one thing we need to remember from calculus is that for a function f of x of y, the cross derivatives are equal. So what that means is if I first take df over dy and take d over dx of that, or I take df over dx and then take d over dy of that, I'm going to get the same derivative out the end, which is d squared f over dx over dy. To take an example here, if my f of x is 2x squared times y, if I first take the derivative with respect to x, my 2x squared becomes 4x. If I first take the derivative with respect to y, I just had a y here, so that will drop out and turn into 1. df over dy is 2x squared. Now I'm going to take the two cross derivatives. So d over dy of d over dx, that's, again, just a derivative with respect to y of this quantity. That is just my nice 4x here. And similarly, if I take the derivative with respect to x of this, 2x squared times 2 is 4x. Again, we're not going to prove it here. This is just an example, but it is a very, very powerful result, and that we're going to use here to figure out some of these very hard to calculate directly quantities. So to apply this to thermodynamics, if I look at dg is v dp minus s dt, dg over dp is going to be equal to, if I look at this equation, dg over dp is going to be equal to volume, right? This is dg over dp at constant temperature. And similarly, if I take dg over dt at constant pressure, this is negative s. Just looking at the equation here, right? dg dp, that's going to be volume. If I keep temperature constant, that term goes away. Same thing in reverse here for dg dt at constant pressure, giving us negative s. Okay, now one more step. If I take dg over dp and take d over dt of that, now this is dv over dt. What do I need to keep constant? The other variable. So I need to keep pressure constant. So dv over dt at constant pressure, because I'm considering free energy a function of pressure and temperature. So when I take a derivative with respect to pressure, I need to hold temperature constant. When I take a derivative with respect to temperature, I need to hold pressure constant. So this is dv over dt at constant pressure. This here, again, is negative s. And I'm going to take d over dp of that. So that's going to give me negative ds dp. And again, since I'm taking derivatives with respect to pressure, that means I need to hold temperature constant there. And again, according to our theorem now, we get, again, this is sort of to me, a pretty stunning sort of result. Again, how does entropy vary with pressure? To me, it wouldn't necessarily have anything to do with how its volume varies with temperature, but it turns out that according to calculus and thermodynamics, just applying the rules, we find this sort of hidden connection between these different quantities. So by our theorem, the underlying derivatives are equal, and so we have, I'm going to go back to black here, maybe, dv over dt at constant pressure is equal to negative ds over dt at constant t. So again, this, we have not, we've calculated this for ideal gases, but we haven't calculated too much for real substances. We've assumed ideal gas behavior and been able to sort of back things out from there. But now we can see that there's actually no problem with calculating it for any substance. All I need to do is look at how volume varies with temperature, and that will actually tell me how entropy varies with pressure. Yeah, again, sort of surprising, but it does turn out to work. So let's do our example. How does entropy vary with pressure for a liquid? So far, we've just assumed that it's equal to its standard conditions entropy. But we can now see how much error this is. For acetone liquid, which at 25 Celsius has this molar volume, the volume changes by 0.105 milliliters per mole Kelvin. So we have basically a constant for how volume changes with temperature at constant pressure here for acetone. Not always the case, but that does make our life sort of easier. So since dV over dt at constant pressure is just basically equal to that constant 0.105 milliliters per mole Kelvin, we can now calculate how the entropy changes with pressure as I crank up the pressure. So what is that? Well, again, we just apply our cross-derived relationship that we just got. dV over dt at constant pressure is equal to negative ds over dp at constant temperature. This here we have, again, I could plug in the number, but I'm just going to call this some constant a for now, since this was basically constant. And then I'm going to say, okay, on this side, I am interested in constant temperature, so I don't need the partial derivatives anymore here. I'm just going to write that as normal differentials. So this is negative ds over dp. And now my calculus here is pretty straightforward. If I multiply both sides by dp, I get a dp. And I'll multiply through by a negative sign is equal to ds. Integrate both sides. Since a is a constant, it will come out of the integral. And again, I just get negative a delta p is equal to delta s. Again, I do have the same sort of units issue I had before. Since a is 0.105 milliliters, I'm going to convert that to liters, but not too bad. Maybe I'll rewrite it this way. Delta S is negative 0.105 milliliters per mole Kelvin times 1 liter over 1,000 milliliters. So this is my A in liters per mole Kelvin. And then my pressure is, I'm going from 1 bar to 11 bar. This has to be 11 right there. Sorry about that. And delta P is 10 bar, 11 minus 1. And then again, I'm in liters bar here, so I need to multiply by 100 joules per liter bar. And when I do that, all my units will cancel nicely. Milliliters. We're still per mole, and we're still per Kelvin, but now my liter and bar will cancel here. And I'll get delta S in joules per mole Kelvin, right? Technically, this is delta S bar, I guess. Getting my bars back on there. Luckily, I don't know why I didn't just do this directly here, because actually everything worked out very conveniently here. I divided by 1,000 and multiplied by 1,000. I don't know why I went to my calculator. And this was just negative 0.105 joules per mole Kelvin. So as I squished down on my acetone, it changed its volume a bit, and that caused this decrease in entropy. So as I increase pressure, this is sort of the normal case when I increase pressure. Even for a liquid, I squeeze the particles sort of closer together and into their sort of more equilibrium state where they have fewer possible arrangements. And so normally as I increase pressure, the entropy decreases because normally as I increase temperature, the volume increases. Normally things expand as they get hotter. And those two things are directly connected here. The molar entropy here, again, for changing a gas under the situations, I saw this huge change in entropy, 19.14. Here I only got a 0.1 change in entropy. So again, much, much smaller. The change in entropy of gases is much, much more significant. And we can see the S naught at 298 is 199.8. We only went down by 0.1. So again, 199.8 to 199.7. Not much difference really at all there, especially compared to the gigantic change in entropy for the gas under those conditions. Okay, this is maybe a good point to sort of stop and see if you can calculate some of these things. We have our sort of nice phase diagram here with all these nice points along the phase diagram. Given the density of ice, this is 0.917. Density of water, 0.9998 at 0. what pressure is required to reduce the melting point to -2 Celsius.